Let's see, how did that work? It's been like, I think 3 weeks or something, 2 weeks, 3 weeks without any stream. Yeah, kind of obvious reasons, right? Baby stuff. And it kind of ended up being more complicated than I thought, even though it's not the first time, right? Um, but yeah, it's complicated. So we'll see. And kind of like I need to warm up again. I was doing before, so before that, I was doing the whole path integral stuff, and I kind of, as a kind of kick off all the streams again, and I'll do my best to kind of do them a bit more regularly as I kind of get my routine back in place. Um, I wanted to kind of like warm up with something, kind of like maybe reading something, and then it just was a coincidence. Yesterday was it yesterday. Dave Bacon, I believe he used to work at Google, and now is it IonQ? I think he's IonQ now. Um, no, no, I'm an incognito on purpose. There you go. Yeah, yeah. I mean, I remember him from the videos. I remember watching some of these videos. Um, and yeah, oh yeah, he's vice president software in IonQ. Okay, cool. Um, and so he posted these. Hey, thank you. Uh, and so he posted these, and I thought it's a 6 minutes read, kind of 1,500 words, like this bit of axiom stuff. And I don't know. I'll just yeah, I think we can read through these and then kind of try to see. I haven't read this at all, so I don't know. See where that takes us, and something about these and measurements and whatnot. Maybe there's a bit of a conversation, like mental conversation we can have about these, and then Wolfram's model as well, which is kind of walking back to all what we did at the very beginning of this project, which was basically try to learn quantum mechanics from the Wolfram's physics project perspective, with a goal to challenge sort of the status quo, challenge sort of the traditional way to learn about this stuff, right? I'll do a break in about 20 minutes or so just to check in how the baby's doing, and we'll see. Good, good, good. So, who is afraid of the church of the larger Hilbert space? Mm, it's a draft, okay. Let me see. Is that readable on screen? I hope so. Can zoom it a little bit more. Yeah, it's in GitHub, and yeah. Let's see. Actually, what else does he have? So yeah, because he's done a lot of the Circ stuff. Okay, so actually keeps the essay the essays in a repo. That's interesting. Whatever. Let's get to the thing. So what exactly is a measurement? That's good because it's the so this is actually from the Wolfram model perspective. Wolfram's physics project. I believe he was even recently in a podcast from, was it Sean Carroll, I think. Yeah, I think Sean Carroll, where he did say that because measurement would be so expensive to implement and quantum computing won't work at all or something like that. Like quantum computers won't really provide the promised speed ups and whatnot, which was a bit weird of a comment. Um, Wait, was there a video? Is that new or I don't think that's a new section. Because I remember this being something along the lines of quantum measurement is how then an observer kind of basically says, well, builds an equivalence mapping between states that are kind of then perceived as the same or something like that. and this being something, of course, at scale, just too expensive. But let's see. So this is a similarly innocuous question. Obviously, you get your tape measure out, wrap it around your waist, and count off how many inches you've added to your growth over the holiday season. But in the world quantum theory, the theory that seems to be the operating system of the universe, when exactly a measurement occurs and exactly when exactly a measurement occurs and exactly what it is, only very oddly defined. For our waistlines, this could be a benefit, but as a scientific theory, it is quite disconcerting. So there might be ways to present quantum theory. There are many ways to present quantum theory. For example, one approach is to start with wave functions and add the Schrodinger wave equation, which governs the time evolution of these wave functions, and equally valid starting point of this is linear algebra. So that's kind of the quantum computing one, right? Which my friend David Hogg likes to remind us is not an algebra. Linear algebra is not an algebra. What does this mean? Anyway, that's not for now. But one of the clearest ways to get at the basics of quantum theory is through a simple set of basic axioms. Probably my favorite version of these are from Preskill's lecture notes. Here Roth paraphrases of these axioms without the measurement axioms. So axiom 1 states R rays in Hilbert space. Axiom 2, observables are self-adjoint operators. Axiom 4, dynamics of a state, evolution in time is a unitary operator. Okay. And when you take two systems and form a composite, the state space of the composite system is a tensor product of the two systems' Hilbert spaces, as we know. But yeah, just missing axiom 3, which is the measurement. And now that's not going to render nicely. That sucks though, but maybe we can take it from Preskill's notes. Oh, they are actually there at page 3. Oh, here are a bit more elaborated. In quantum mechanics, observe is a self-adjoint operator. An operator is a linear map taking vectors to vectors. Yeah. So, and what was self-adjoint? I hate it that it just goes with the German results because I'm in Germany when I'm using the incognito mode. Maybe I should just. There's no way to change that. Change the language to English. Self-adjoint operator that its own adjoint. If I kind of forgot what all these kind of terms mean, to be honest. Operator on that space grounded rule. Operators. Yeah, whatever. It's like it's sort of the like a counterpart of that operator that it's sort of a way sort of a way of like think about like not an inverse but like a sort of a complement to that operator. Consider the operator A that takes from this space to this space. So the adjoint is the one that's kind of the opposite. Oh, backwards. Yeah. So probably that, meaning that whatever. To be honest, I don't know why. Why is that a defining property of an observable? That's something to take a look at. Why is that a defining property of an observable? Why does an observable need to be a self-adjoined? Maybe someone in okay, yeah, no, it's not that all self-adjoined, but the other way around. Like that's true, right? Quora. I haven't visited Quora for a long time. Commuters always have real eigenvalues. The eigenvalues are what is measured by an observable operator. Commute are normal. Perhaps guys the probability of the problematic. The fact that commuters is a normal means that the amount vector is known as probability density. Yeah, so this is just a technicality. Okay, so this is just a technicality, meaning that it's just because it's the way that mathematically work with the states, right? And so if your candidate observable is not fulfilling these, then you're not gonna then it just basically gives you results that are not observable, or they're not like there wouldn't be things you can observe, I guess. Mm. They have real eigenvalues. Since eigenvalues are what is measured by an observable operator, we want these values to be real. So no complex or something like that. Now, universe, all measured values are real, non-complex with no imaginary part. So that makes sense. And matrices that commute with their adjoined are normal. So clearly they satisfy the normal matrices are positive semi-definite when multiplied by where v is a state vector, they get a new state vector u. We want the elements of u to be u squared to be probabilities, and as you perhaps guessed, probabilities would be really problematic. Minus e probabilities would be really problematic. Yeah, okay. So it just a technicality, because when we want to apply these to a state, then we want these to preserve the notion of the output is a valid wave function, or a wave function by a state vector, and okay. Yeah, cool. Axiom 3. A measurement is a process in which information about the state of a physical system is acquired by an observer. And it's always, the problem is always what the observer is and what the measurement process, like what counts as an observer, what counts as a measurement process. In quantum mechanics, the measurement of an observable prepares an observable A prepares an eigenstate of A, and the observer learns the value of the corresponding eigenvalue. If the quantum state just prior to the measurement, I guess I need, because that's just LaTeX stuff, right? Axiom 3, measurement. Okay, so short enough, it's probably. So it's a process in which information about the state of a physical system is acquired by an observer. In quantum mechanics, the measurement of an observer A prepares an eigenstate of A, and the observer learns the value of the corresponding eigenvalue. If the quantum state just prior to the measurement is that state vector, like psi, then the outcome AN is obtained with a priori probability. The probability of AN, which is the I guess that's the energy. So you square the thing, right? And then because that's the expectation value. So if the outcome AN is attained, then the normalized quantum state just after the measurement is this divided by that. If the measurement is immediately repeated, then according to this rule, the same outcome is obtained again. With probability 1, if many identically prepared systems are measured, each described by the state psi, then the expectation value of the outcome is the sum of expectation values, right? Okay. A. So what this is saying is basically, so this action, so what this is saying basically is you've got probabilities of observing one of the eigenstates, or no, eigenvalues, sorry. And the thing is, once you observe it, then there is some sort of update, or there's, kind of the measurements you would do after that would always give you that same eigenvalue with probability 1. Yeah. So this axiom takes out more length on the page than the other axioms, but it also shows out a lot of terminology. First of all, there's an observer. What is that? And it describes measurement as a process. But what makes it different? What makes it a different process than the normal unitary dynamics of axiom 4? That's a good question, actually. Like, what makes it different than just pure time evolution, right? All of these should make you a little uncomfortable. Like in Wolfram's thing, right? Let's see what they say here. So, summary, the crime measurement can work in a concept models. Here, give some more detail. In a sense, the key to quantum measurement is reconciling our notion that definite things happen in the universe with the formalism of quantum mechanics, or the branching structure of the multiway system. But if definite things are going to happen, what might they be? Consider example of a string substitution system. Consider the rule A to A, B to A. We could imagine a simple classical procedure for evolving according to this rule, in which we do all the updates we can, say based on the left right as can at each step. But in fact, we know that there are many other possibilities that can represent the multiway system, right? So most of the states that appear in the multiway system, however, are unfinished, in the sense that there are additional independent updates that can consistently be done on them. For example, with the rule A, BA, there are 4 separate updates that can be applied to AAA. Yeah. But none of these updates depend on the others, so they can in effect all be done together, giving the result. Put another way, all of these updates involve space-like separated parts of the string, so that they all are all casually independent, and can all consistently be carried out at the same time. States. The view of quantum measurement is that it is an attempt to describe multiway systems using generational states. Okay. Sometimes there may be a unique classical path. Sometimes there may be several outcomes from measurements corresponding to several generational states. Let's consider the actual process of doing an experiment on a multiway system. Okay, so here they talk about doing an experiment on a multiway system or a quantum system. So you want to describe that in terms of a limited number of generational states without having to track all the different branches in the multiway system. Quantum states, a construct we form by assembling these states, can be thought of as a superposition of the states. So causal invariance then implies that through the evolution of the multiway system, any such superposition will then actually become a single quantum state. Like, yeah, meaning like in reality, you cannot have a superposition, right? So if you have a superposition, it means they just must all collapse to one state. Kind of that's the measurement, right? In some sense, the observer did nothing. They just notionally identified the collection of states. It was the actual evolution of the system that produced a specific combined state. Morpholation 1 is going to use to represent the progress of time. In this freedom-typical quantum observation frame, it is critical in being able to maintain a view in which one imagines definite things to happen in the system. Yeah, that's kind of the basis, right? Oh god, that's too long of a... I don't know if a particular state is something the observer can choose to do in their description of the system, but the crucial point is that the actual dynamics of evolution causes a choice to have implications. Freedom will see here is the manifestation of this phenomenon. But one can also imagine being somehow outside the system. For example, one might try to set up a quantum experiment in which the construction of the system somehow makes it natural to maintain a frozen time foliation, the picture below. Really happens. It depends on the sense of relationship as a system. Traditional thinking about quantum measurement, one is interested in the impressions of observers who are in effect embedded in the system. And for them, the coordinate systems they choose in effect defines their reality. There's a lot of warm up to get here, to get somewhere. The foliations have to construct. In effect, we're having to construct foliations to reverse engineer the actual evolution of the multiwave system. Because in effect, we're asking the observer to outcompute the system itself. Yeah, we can expect the evolution of the multiwave system, say for one of the models, which will correspond to a reducible computation, to do more computation and maintain description. To maintain description, so the coherence will be inevitable. That didn't tell me anything, but maybe it's in that section before. Okay, quick coffee break. Yeah. Back there. Sounds back, yeah. Yeah, whatever. That it's just there's nothing about measurement in here though. Maybe here. So one can potentially think of a different foliation as being a different quantum observation frame or quantum frame analogous to the different reference frames one considers in studying spacetime. In the case of something like an inertial frame, one is effectively defining how an observer will sample different parts of the space over the course of time. In a quantum observation frame, one might have a more elaborate specification involving sampling particular states of relevance to some measurement or another. Yeah, but that's all that it says, right? One feature of traditional quantum information is the concept of making measurements that effectively reduce collections of states. As existing in a multi-way system to what is basically a single state, analogous to what would be seen in classical single path evolution from the point of view of quantum observation frames, one can think of such a measurement as being achieved by sculpting the quantum observation frame to effectively pick out a single state in the multi-way system. We'll discuss in more detail below. Meshitara universe is based on a simple string substitution system, such as A, A, B. If we start from state AA, there's a picture above. The multi-way evolution from the state immediately leads to multiple outcomes associated with different updating events. But let us say that we just wanted to do some kind of classical summary of evolution, ignoring all these different branches. One might trace individual updates, but trace the generational states. So the states of like when you apply all the rules at once, right? In which all updates can consistently be applied together, have been applied, and with a particular rule shown here, we then get a sequence of states highlighted above. And as we'll discuss below, they can indeed consider these generational states correspond to definite classical states of the system that can consider thought of as potential results of a measurement. Covariance makes a crucial contribution because it implies that all such differences. To us as observers, is a sense the state we're looking for. It is the result of our measurement. So it's generational states. That's what they're saying. But whatever. So all of these should make you a little uncomfortable. The great thing about quantum theory, however, is that even with these sort of ambiguities, there's always been a way to just make them work when you hit the real world of experiments. For the experts in this area, I'm sure what I'm saying is naive, but I believe even they will have a feeling of encountering something that is somehow mysterious when encountering the measurement axiom. The measurement axiom is somehow how things become, how they transition into something more permanent, existing as records of what happened. There are a group of physicists, loosely we call them quantum foundation researchers, who spend a lot of time thinking hard about quantum theory and what it means or what it tells us, or how to live with quantum theory and not go insane. What is a measurement and how does it mesh with the other axioms of quantum theory is one of these areas in which quantum foundation folk have spent a lot of time investigating. I've been lucky enough to work a bit on these back in my younger days. So this actual paper reference. Bell correlations. In my spare time, I still think a lot about these. Nothing says crank like being a software engineer thinking about the foundations of quantum theory. People whose papers I will read whenever they come out include Matthew Leifer, Robert Speckens, Chris Fuchs, and more. Down those links is a lot of head scratching and some well-earned moments of clarity. In reading that literature and thinking about some of these problems myself, one thing that strikes me is that there's a good deal of work in that arena, which works very directly with a sort of variation on the axiomized version of quantum theory. In this approach, one considers preparation of states, evolutions, and measurements as separate processes. Preparation of states, evolutions, and measurements as separate processes. Sometimes measurement and preparation are combined. In this approach, one thinks a lot about the measurement results and how they correspond to the reality or unreality of the quantum state, contextuality, and quantum non-locality. There's a lot to be said for this approach. It leads to Bell inequalities, experiments on contextuality, and results about the epistemic, well, that's pronounced, or non-epistemic nature of quantum theory. But it does make a particular sleight of hand in that it does make one think about preparation, dynamics, and measurement as sort of separate. So enter religion to the debate. In quantum information, there is only one church, and that church is the church of the larger Hilbert space. This phrase, kind of the church of the larger Hilbert space, was coined by John Smolin to describe a very useful tool. In particular, it describes going from the system under study to a larger system that contains the original system as a tool for proving things about the original system. This can be done for both quantum states but also quantum channels. And it turns out to be an amazingly useful tool. For quantum states, this tool is used when working with mixed states. The mixed state is described, unlike in axiom 1 above, by a density matrix. The interesting thing about the density matrix is that it can be purified. That is, a mixed state can be thought of as a pure state in a larger system. I mean, I never thought about these, but it kind of makes sense, right? It's like the way that entanglement, like it's the way, if you kind of flip that statement, right, and think about, I have a quantum state that is an entangled quantum state, and I can look at their subsystems and think of their states as being mixed, right? So so you can think of these being mixed. Like if I take a look at the density matrix of these and the density matrix of these, but if I look at the full state, the chance, it's a 50-50 chance. It's just the way, here you've got something that it's at the system level, right? You have at the 2-qubit level, you have like a quantum state that's like the 0, 0 plus 1, 1. But each subsystem can be either 0 or 1 with probability 50%, but it behaves like a mixed state. It behaves like, doesn't mean it's not that it is necessarily a mixed state or whatever. I got in trouble for saying something like that recently in Twitter, but yeah, okay, so that statement makes sense. Never thought about these the other way around, right? So when you have a mixed state, you can think of sort of going one level upper and think about this state, this system being embedded in a bigger system, and then yeah, so it's purified. Connecting back now onto those axioms, it strikes me that when one thinks about preparations, evolutions, and measurements separately, one has to be able to think and make sure that your reasoning is robust to the church of the larger Hilbert space. In particular, whatever one is doing for these setups, which delineate into 3 separate processes, then one needs to be worried that these, in fact, are actually working in larger space. That is, when reasoning about these as separate objects, one needs to be careful that these arises from the church of logical space trick. As a concrete example, consider a measurement of a qubit in the computational basis. One can describe this as the above axiom 3 applied to an observable with different values. For the, I guess that's ket0 and ket1 eigenvectors. If one is then reasoning about measurement from within the context of a preparation unitary measurement framework, then one will need to handle this measurement. But one can also think about this measurement as a process in which one attaches another qubit to the system, initially in the 0 state, applies a control knot from the original qubit to this qubit. If the second qubit is never touched again, then the first system will behave as if it was measured. Wait, what? So I have an unknown, so a qubit in an unknown state. I attach another qubit that's at the 0 state, so this is known. I apply a control knot controlling on the original qubit. And so if the second qubit is never touched again, the first system will behave as if it was measured. Yeah, okay, so it will behave. Yeah, I mean that's what we did here, right? So this is the state here, right? So if I introduce, let's say I don't know what that is, right? It's a question, like it's like a mystery box or whatever. So when I introduce this one, and then I do a control knot, then that behaves like if it was measured. It's either these or these. but there's no quantumness to it. It's not a superposition anymore, right? By thinking about the density matrix after the measurement is as a purification in a larger pure state, the church trick, one has transformed the original setup into something that doesn't really contain measurement, assuming here that the measurement outcome isn't really used, just to keep things simple. So one really needs to explain what your theory says about the just unitary evolution part of the setup and give this measurement result. I guess what Dave's saying here is that if you think about if what you're doing is you're thinking about these three separate processes as separate entities, right? And now you kind of have this problem where if you use this church trick, now you have something that looks like a measurement, but it's not a measurement. It's actually evolution. Um, yeah. So and this is, I think, an important issue which those trying to explain quantum theory or see deeper into its interpretation have to overcome. They need to be able to deal with the case of everything being unitary or possibly everything being a quantum operation. So who's afraid of the Church of the Hilbert, a large Hilbert space? I think everyone who wants to think about quantum theory in a theory that separates preparation, dynamics, and measurement and studies them separately should be scared. One needs to respect the Church, that we can get much of what we do by working in a larger state space, and reasoning about foundations should be wary of these, maybe even going so far as to say that we should not make these separations. Down that path, we may find many more interpretation of quantum theory, but that's another discussion. Yeah, but that's a discussion I'd love to have. I mean, but because that's like what the many world people say, right? It's like they are saying that entanglement is measurement. That when you get entangled, like and that's kind of what's happening here. You get entangled, right? And so you'll either be you will only see part of the wave function, right? Because if this guy if this qubit is turns out to be zero when you measure it, then you know that that's zero. That's kind of your reality within the universal wave function that we're modeling here was just that toy system. And if it's one, then it's going to be one. So you kind of, yeah, from your perspective within that system, if this is the system and this is the observer, imagine that that's the observer, right? The entanglement, that's a measurement, or it behaves like a measurement. Cool. No, that was a nice read. Definitely a nice read. But then here, so here what they keep talking about like is the generational states being the states that you can measure, right? The generational states being sort of the state where everything happens, right? So you do all the updates that you can. So here you start with an A, so you get AB, and now you go to AB, so you apply 1, and you have A, B, B, right? And then the B is an A. The thing is, I kind of try to, I'm kind of like starting to realize that a way that one can see the rules is as in like the path integral formulation, the the propagator, right? So the probabilities of transitioning from one state to another. Maybe. So then there's kind of certain probabilities of, so there's probabilities attached to the, but then there will be probabilities attached to the rules being applied. And I'm not so sure if that's what they do. Because like one thing that I like about this whole concept here is that you kind of keep throughout the time like the concept of this system and also the sub parts of the system. And the rules really apply to the sub parts of the system. So how the sub parts of the system can evolve. And I'm not so sure if this is something that quantum mechanics allows to be defined. And maybe it's a question for quantum Twitter. So how you from I basically say so I basically say, can I go? Let me see. I'll write it later. But can I just basically say, does the quantum mechanics formalism, even just let's just focus to with the path integral formulation, right? Like if I have a system, can I define its dynamics by defining the dynamics of the subsystems only? Yeah, that would be a way to phrase it because that's something interesting. That looks like a thing to dig into. Because I remember that still was struggling to understand like how would that map to like you know quantum computing basics like 0, 1 cats type of evolution. And so you would evolve the different things, right? But then what are the generational states mapping to? Because basically what they're saying is the generational states are the potential states that you can measure. But then they start talking about foliations, as in like that's how you define the time evolving. These generation states have been highlighted and a foliation has been selected that essentially freezes time. Around a particular generational state. In effect, the observer is choosing a quantum observation frame in which there is a definite classical outcome for the behavior of the system. I'm not sure I understand the freezing time here, so I might have to recap these as well. But definitely something interesting to think about because I now I'm trying I'm things start to come back to mind like from the videos before September. So about the path integral and trying to understand what the path integral formalism would help me understand quantum entanglement stuff and ways to model entanglement. And actually, that is a good question that it didn't come to me before. It hadn't come to me before. So it's the question is what I just said before, right? So saying, can we define the dynamics of a system by defining the dynamics of the subsystems only? Because that could be an idea. That could be an idea. Or will we then have trouble? Like how are then 2-qubit operations defined like that, right? Yeah. I mean, which I still don't quite get it. Like, I mean, the quantum operations at the end, what you're doing is, when you think about gates and whatnot, is a way to break down. I mean, those are quantum gates, aren't they? Because this is a way that you're breaking down a Hamiltonian, right? That it just tells you how the whole system behaves, and then you break it down into quantum operations, which tells you how the subsystems behave. But from a path integral perspective, you have the propagator. But can you have propagators for the subsystems? That will be, can you have because those would be the analog of gates, right? But that's like good luck. Good luck, man. Cool. Not cool, I guess. But yo, I'll think about these. Anyway, that was good. Yeah, that was a good warm up. Um, Thanks to Dave Bacon for these awesome lines. Yeah, kind of got me going again with the thinking here. So really good stuff. Yeah. Um, yeah, I don't know. To be honest, I think like outside of these, from a more organizational perspective, I really want to try to get on a regular schedule because that's going to be beneficial for me just to keep a good pace. And it's going to be beneficial for everyone, anyone who's interested in the streams. So hopefully I can do that. Yeah. Bye.